All right, let's get right into it. Contact tracing. It's one of our best weapons in a pandemic. It's like a real-time detective story trying to stop a virus cold. But here's the thing. It has this hidden vulnerability, and honestly, it's pretty scary.
Because we've all seen this happen, right? One minute, it looks like public health officials have an outbreak under control. And the next, bam, it's chaos. So what gives? What's the hidden weak link that makes this vital tool just shatter, seemingly without warning?
To figure out why it breaks, we first got to understand what it's trying to do. The whole point of contact tracing is to make the invisible visible. You're literally trying to follow the ghost-like trail a virus leaves as it jumps from person to person. And it is a frantic race against the clock. Imagine this. Investigators have to find someone who's sick, and then, based on that person's memory, track down every single person they might have breathed near. It's a huge, manual effort that relies completely on people and resources.
Now, obviously, you can't study this with trial and error in the middle of a real crisis. So to find the actual breaking point, scientists did something incredibly clever. They built their own digital world to play out the disaster.
They put together this massive model, basically a digital twin of two huge South Korean cities, Seoul and Busan. And they filled these virtual cities with millions of digital people just living their normal everyday lives. And I mean, this thing was detailed. We're talking millions of people interacting across 5 totally different social circles. You know, the people you live with, your coworkers, your classmates, your friends, and even just random people in your neighborhood. Every layer of our social lives was baked right in.
So they ran outbreak after outbreak in this virtual world. And in doing so, they found something absolutely critical. It turns out that when contact tracing fails, it's not just one kind of failure. Nope. There are 2 very different ways information gets lost, and they have wildly different results.
Okay, the first type is what they call infector omission, or IO for short. This is the big one. This is when an infected person is just completely missed by the system. They're a ghost. Think of it like a detective losing the entire case file for a prime suspect. The trail and everyone that person infected just goes completely cold.
And the damage from this is just catastrophic. An entire branch of the virus's family tree just, poof, vanishes from the map. The virus is now spreading in the shadows, and the tracers don't even know it's happening.
Then you have the second type, contact omission, or CO. This is different. Here, the infected person is found, they're on the map, but maybe they forget to mention a few people they saw. Going back to our detective, this is like having the main case file, but a couple of phone numbers inside are smudged and you just can't read them.
And the difference in the fallout is just massive. With this kind of mistake, at least the main infected person is known. You still have the core of that transmission chain. A few branches might disappear, sure. It's definitely a problem, but it's not the same world-ending catastrophe as the first type.
So we have these 2 kinds of failure. One sounds worse than the other. But the real question is, how much worse? Well, the answer the simulation gave is what's really shocking. It's not a gradual slide into failure. It's a cliff, a tipping point.
The researchers said it perfectly in their paper. Missing entire infected people, that's the IO scenario, causes substantially stronger and more abrupt changes. In other words, the system doesn't just get a little weaker. It shatters. It completely collapses.
And this is the number that defines that collapse. 4%. In a massive, dense city like Seoul, if contact tracers miss just 4% of all infected people, the whole system falls off a cliff. The ability to contain the outbreak, gone. Just 4 out of every 100 cases slipping through the crack. And the impact of crossing that line is just staggering. Stay below 4% and things are mostly contained. But the second you go over it, the number of infections doesn't just creep up, it explodes. It's not a gradual hill, it's a sheer drop. The system breaks.
So, you might be thinking, is 4% the magic number for every city on Earth? Is that the universal breaking point? Well, the researchers wondered the same thing, so they ran the simulation in a completely different environment.
They compared Seoul, a megacity with almost 10 million people, to Busan, which is smaller and less dense, with about 3.3 million. And the results? Totally different. Busan was way more resilient. Its tipping point wasn't 4%, it was 10%. Which tells us something huge. Local conditions, especially population density, really, really matter.
Now, this isn't just some fascinating computer model. The lessons learned from this virtual world have profound life-saving implications for how we need to handle the next real-world pandemic.
And here's the absolute #1 lesson. When your resources are stretched thin, the main priority has to be finding every last infected person.
It is way, way better to find 100% of the infected people and miss a few of their contacts than it is to miss even a tiny percentage of those initial infectors. Preventing that infector omission, that is job one.
The study also brought another danger to light. They measured something they call the network diameter. A simple way to think about it is, what's the longest unbroken chain of infections in an outbreak? It's like the virus's longest family tree.
When tracing fails, especially when you miss those initial infectors, that chain just gets longer and longer. The virus digs deeper into the population. And every new infection, every new link in that chain is another roll of the dice, another chance for the virus to replicate and maybe, just maybe, mutate into something even worse.
And that leaves us with one last, really powerful question to think about. We usually see contact tracing as a tool to just stop the current spread. But this research suggests it might be even more critical than that. By keeping those infection chains short and contained, could we not only control the outbreak we're in, but actually prevent the next dangerous variant from ever being born in the first place?